Okay, let's get started. That was enough wait time. So today is our formally starting of the classes, because yesterday was more of like a demo and getting to know each other, or understanding our CCNA roadmap and setting up the expectation for everyone. Now we start from module 1, and I hope everyone has got their Netacad issues resolved. Everyone can access their Netacad accounts and follow along. So CCNA Introduction to Networks is the first course. We are in 3 parts. We will complete CCNA in 3 parts in Netacad catalog, as we saw. So CCNA, this is an introduction stuff that we have already talked about in our previous demo class. So I'm just going to go through it very quickly. We just reiterate that CCNA in Netacad catalog is comprised of 3 courses. So CCNA Introduction to Networks, CCNA Switching, Routing, and Wireless Essentials, CCNA Enterprise Networking, Security, and Automation. So we plan to spend 1 month on each of it. So 1 month on this, 1 month on this, 1 month on this. And when you complete all these 3 courses, that's when you can really say that you have completed the entire course for the Cisco Certified Network Associate certification, which will cover all the exam topics that we yesterday saw. And then you would have to prepare for the exam and do the examination if you want to get certified, for which you will register for an exam. So the first part, so we are in Introduction to Networks. That is the first course of the 3 courses. Inside this first course, we have 17 modules, and today we are talking about the module 1, which is networking today. The objective of this module is to just get to know what networking in general is, why it's important, what does it consist of, what are the generic items that come together, connect together, how do they connect together to build a small network, and that's the overall objective, so that you have an understanding of the basics of networking. So we will not be going we'll be not doing a deep dive in anything, so there's nothing technical today. It's more of like getting to know networking in general. So we will understand how networks are important in our life, what are the different components that make up a network, or a computer network in specific. So whenever you see networks in this course, just understand that we are talking specifically about a computer network. Network could be of anything. We are talking about a network of computers. Network just means things that are connecting or jumbled up together, that becomes a network. So network could be a human network. When we communicate with each other, come together in a group and benefit from each other or collaborate with each other, that's also called a network, but that's a human network. Here, we're always talking about computer networks. So computer network, how does computer network affect our life? How does a computer network, what are the components of computer network? And how do we actually represent these computer networks on a paper, on a page, or on a dashboard, or anything, to understand or showcase or communicate about those computer networks? So there are a bunch of ways we can draw networks. Drawing and documentation is a very important part of computer networks. So we will see what are the different ways we can do that. And we have different types of computer networks. For example, small office, home office, local area network, and WAN network. We'll see what's the difference between them. And then the internet connections, with which you all are familiar because everyone is using the internet, but we will go through it using high-level discussion, how internet is made up of these different types of computer network. We'll go through quick installation, download installation of Packet Tracer, and see how Packet Tracer can help us understand all the things that we're talking about. And that's where we will be really modeling our computer networks. That's where we will be really practicing on our network. So everything we're talking about, that all the things can be done in Packet Tracer and can be seen and can be represented and can be practiced on. Finally, to end this module, we will talk about different aspects of networks, in which we have what we call a reliable network. So meaning that we don't just need a computer network to be there. We want it to be a reliable computer network so that we can rely on it because our lives depend on it. Okay, so there are some characteristics of reliable network, which is fault tolerance, scalability, quality of service, and security. And finally, we'll look at the network trends, where the networks are going. What are the latest trends like cloud networking or AI networking or small devices communicating with internet? So what are the different trends that these days are coming in, right? Finally, well, it's another final. So final is never ending. So network security is also important. Since we talked about that computer networks, our lives depend on computer networks. That also means that we need to make our networks very secure, because there are threats out there, not just for networks. I mean, they are directly threats for the networks, but they eventually threaten our lives as well, because our lives are dependent on these networks these days. Okay, so how does the computer network affect our lives? Well, that's pretty easy to understand. We use computer networks the whole time, everywhere. We just don't think about it that these are the computer networks. So whenever you open up your phone or a computer and you're searching something, you're talking to ChatGPT, or you're just Googling stuff, or watching a video on a YouTube, you're using a computer network. Okay, everything you're doing on a phone, on the internet, that is supported because there is that's there, and it's working because of a computer network, because there's a huge computer network, and there are huge connectivity problems that have been solved by network engineers for you around the globe, which is why you can just open up your phone and type in YouTube and the video is playing. That's because of network. Okay, so that's just entertainment. So YouTube is just the entertainment part of the network that you daily use. If you go to hospitals, your records are there, your history is there, there are machines, there are MRI machines, there are dialysis machines. Everything is connected to the network, and that's how they're working. So all the modern equipment depends on computer network. If your network goes down in your hospital, you're not getting treated. So one is the entertainment part that you always see, that's made possible because of network. Another is life-saving part of equipments that you use in the hospital that are saving lives. They're also dependent on network. Okay? Similarly, AI, so there are a lot of use cases for AI and benefits of AI. It cannot exist without a network. Computer network is the basic infrastructure that you need whenever you talk about any application or modern equipment to use. Okay, so we talked about these applications and stuff that are dependent on the network. The creation of cloud let us store document pictures and access them anywhere, anytime. So whenever you hear a term cloud, for example, Google Drive, where you save your files, or anything, Microsoft OneDrive. I mean, I'm giving those examples of the cloud because someone is asking a question. What about knowledge part? I mean, phone is a power. Yeah, Peter, you're right. So everything. So think about a digital library. That's also, you are dependent on the network. So everything runs on network. Okay, even the cloud. I don't know how much you have an experience with communicating on a cloud or using the cloud, but even if you don't have any experience, you must know Google Drive, or saving your phone data or pictures on the cloud using iCloud. So when you're saving your phone on the cloud, saving your files or photos on the cloud, that is also that's also a computer network. The storage is supported by a computer network. Because there's a network, that's why you are able to upload your data to the cloud. Okay. Yeah. So everything. So when I say network, I basically mean internet, right? So internet is also a network, and that's what we are going to cover in this module to understand like why I'm saying like internet or a network. It's the same thing. When you're talking about computer networks, internet is basically a computer network. Okay. Okay, my screen share, I think it stopped. Let me see why it stopped. Okay, I think I'm sharing again, right? Let me know if you can see it again. Okay, yeah. Okay, so as a network engineer, that would be your daily job to understand, to design, build, maintain, operate, and automate networks. And that means internet is depending on you. So when you become a network engineer, when you become a CCNA and you get a job, you get a network support engineer, and eventually become a network engineer, fully network engineer, what do you do in your daily job? That is your job. You design networks, computer networks, and then you build them and deploy them. And once you deploy them, it's not a one-time work that you deployed and it start working and then you leave it and you never touch it again. No, when you build networks, they need to be maintained. They need to be operated on. They have issues every day and you have to solve that issue. That's the maintenance part then you have to do. And you operate them on daily basis. There are changes need to be made on daily basis. There needs to be upgrades. There needs to be devices that are failing that needs to be swapped. There are ports that fails that need to be changed. There are configuration, there are misconfiguration, there are software upgrades, there are licenses issues. There are a bunch of issues, hundreds of issues that comes up in the running network that needs to be dealt with, troubleshooted with. That's what you would do when you become a network engineer. And automate networks. You would also, these days, need to learn some basic automation skills to build these networks so that you are not doing everything manually. And that's where next AI is coming in next in collaboration with the automations, that you can use AI agents to use the network automation to configure devices or troubleshoot devices and automatically fix things. That's where we are going. Okay. So that is just the importance of AI can replace a network engineer or NOC engineer, probably maybe this year, maybe next year. But that doesn't mean the jobs are going away. It only means that jobs nature is changing. That's all. So if AI agent can replace a NOC engineer, somebody has to design an AI agent to do that, right? So you become that designer, a network engineer who designs those AI agents to get that job then, right? Okay. So what are the different components that make up of a network? We talked about that the internet is a network, right? So how is an internet a network? What are the devices that make up of this internet or a computer network? Well, the first one is the host. So networks have many components. One of them, the major part of is the host, which could be anything like an end device, like your mobile phone, a tablet, a computer, a laptop, any IoT device like your fridge or washing machine that is able to connect to internet, because now they have Wi-Fi chips as well and they can connect to the Wi-Fi. Your air conditioning unit can connect to the internet. That's also a host. So anything that can connect to the internet or a network is basically an end device that can generate some traffic and send it towards the internet or other computers or other machines. That is a host. It could be anything, an end device, intermediary device, the devices that let you get connected together. For example, your home router, that is an intermediary device. That's also a network device, right? And then there are cables that connect two computers together, like RG, like Ethernet cable or fiber optics, or even the electromagnetic waves, the Wi-Fi, which is without cable, it's wireless. That's these are physical media that connect these devices. Okay. So all computers that are connecting to a network and participate directly in the network communication are classified as a host. As an example, I told you, like your laptop, phones, computers, your fridge, your washing machine, your AC unit, anything that's connecting to the network is and generating data is basically a host, an end device. Okay. So that's what that's saying. So it includes computers, smartphones, printers, or even smart TV. Yeah, I forgot about smart TV. That's a very common one these days at home. So these are also hosts. So now you understand what a host is. When we talk in computer terms, a host means any end device. Any of those things that can connect to the internet or a network and send data is a host. Now, a host could be of two types. We have further categories of host. Most of the hosts that you know are basically clients. So when you're using a phone, your TV or a computer or laptop or tablet or washing machine, they're all, in most cases, acting as a client. What is a client? Well, when a host or computer requests services or data from another device over the internet, then that computer or host is basically a client. And that's what our computers always do. They just request services from internet. You always request data or watching YouTube over your phone, so you're requesting data from YouTube. You're requesting data from Google. You're requesting data from ChatGPT. Your TV is requesting data from YouTube or other applications. So your devices are always requesting something. They're not providing anything to anyone. So they are clients. They always consume services. On the other hand, we have some devices that act like servers. So usually you don't see servers at home. Usually servers are at the data centers in corporate environments, like Google server. So Google servers are also machine. They're like they're not normal PC, they're specialized PCs, but essentially they are computers, right? They just have more CPU, more RAM, and more storage, but basically they are computers. Why do they have more CPU, more RAM, and more storage? Because they need to have a lot of data saved on them. They need to process a lot of data. For example, like a YouTube server, it would have a whole storage unit with it to store all these videos somewhere, right? And your computer becomes a client who requests from Google's computer to watch a video. In that communication pattern, in that context, your computer is acting as a client and the Google's computer is acting as a server. That's one example of server. You can have servers at your home as well. Your normal computer can become a server as well if you install a particular software like a print server. So your computer can become a print server, your computer can become a file server. It's totally dependent on the role of a software that's installed on the computer. So any computer, even your phone, can become a server if it starts providing some sort of services to another computer. Okay. So client and server software usually run on separate computers, but it's possible to make them run on the same time in the same computer as well. So in small networks, we almost always have small businesses or at homes. We have same computer that functions as a server and a client at the same time. We can just install different softwares on it and make them work that way. Okay, so whenever you do that, so you have a computer, you just connect it, let's say it's not connected, but you have a Wi-Fi at your home or your office, right? It has two antennas. So you have a computer, you have a phone, you have tablets. They're all connecting via Wi-Fi to each other. So it is possible in this small network that you can install a specific software, like you don't have to install anything. Like if you have a Windows computer and you right click on a folder and you share that folder with the network and protect it with a username and password usually as well, then these computers and laptops can go to their browser, put in the IP of your computer, and they will be able to access that file share via the network that you shared on your computer. In that case, what do we say? Like in this context, your computer just became a file server. So similarly, we can have another computer connected to the same Wi-Fi can become a print server. You just install the print driver and connect a printer to this computer, and then other computers can send requests to this computer to print a page. In this case, this computer has become a print server, and this computer just became a file server. So you can see when this computer, let's call it computer A, was requesting the computer B to print a page, in this context, This computer was a client, computer B was a server. But at the same time, computer B can send a request to computer A to access a file. In that moment, computer B was a client and computer A was a server because A was serving some services to the B. So that's what we mean. In small networks, home networks, or small offices, a computer can take both roles at the same time. It could be a client, it could be a server at the same time. And this type of a network, we call it a peer-to-peer network. We call it a peer-to-peer network. All the computers act like peers, like buddies, like friends. There's no hard-coded requirement from anyone that you specifically become a server and you only do services and nothing else, and everyone else would be client. There's no hard definitions in this environment. Everyone can become a server, everyone can become a client whenever needed, because the needs are very small. So we don't make those differentiations. In Windows operating systems, this kind of setup is also called workgroup, which is a very old concept, usually not used a lot, but it's good to know. So I just gave you this example of a file share and a print share, and it is okay in a small network to work like this. In a peer-to-peer network, it has advantage. It's easy to set up. You don't have to do anything special. You just all the normal computers. You buy all the normal computers. They have normal operating system. You can share files with each other. You can share printer with each other, and everyone is. We call this a peer-to-peer network, and you get things done. It's less complex. You don't have to buy specialized software or do anything. Used for simple tasks like transferring file or sharing printers, but it has disadvantages. The disadvantage is that you don't have any centralized administration. What do we mean by that? What we mean is that you don't have a specific computer where all the services are placed. So if there is an issue in a print server, you have to go to the print server computer to find out what is the issue. If there is an issue with file sharing services, you have to go to the file sharing computer and see what the issue is. And each computer would have different account, different logins. Each computer would be placed in a different room or different floor. It could be anywhere, right? So it's not centralized. It is not secure either. Where's my mouse? So it's not secure because each computer needs to be secured separately with separate softwares, antiviruses, anti-malware softwares, separate username and password, and they have to be managed separately. It's not scalable, meaning you cannot, when you have a lot of clients, a lot of employees, and a lot of computers, this solution doesn't work anymore because you have to now remember IP addresses, if you're sharing files with different computers from different computers, or if there are too many printers and too many print servers, which one to select, which one is in which room. You kind of start running into these problems once you have more than, like, let's say 10 people in an office. So maybe this is a good solution for 5 people or 10 people. You don't have to do anything special, just normal computers and normal devices, normal Wi-Fi router, and everything is doing fine. But it wouldn't work if you had 20 users or 50 users. So in major corporates, in major buildings, there are thousands of users, 5,000, 50,000. Think about Facebook, think about Microsoft, right? So this solution doesn't work for them. And obviously performance is slower. So what do? Well, we go to the client server model. This is the one that you would be seeing in the organization when you go to any modern network. They follow the client server model. They don't follow the peer-to-peer. You'd only see this peer-to-peer model at your home or in a very, very small office, okay? So in a client server model, we have a clear separation of roles. There has to be specific devices that are called client, which always request services, and there has to be specific devices or machines that are called servers, which always provide services. They don't do both, okay? So clients, who are the clients? Clients are those devices who are always requesting resources or services from someone. For example, you open up a browser and you type in some address to access a file share, you are always a client. Do you have files to share with someone else? No, you don't do that, okay? So servers are the computers which will be hosting those files that everybody needs. And that's why they're called servers. So on the internet, you can think of Facebook, Google, or YouTube, who has servers, and you're always requesting services from them. It could be said the same thing in your office. So if you take the example of office and extend that, like how would a client server model look like in an office? Well, in office, so everyone has a computer. So let's say there are 10 or 20 employees, everyone has a computer in their own room, or they're sitting in their own floors. They have computers, phones, tablets, and everything. So we would build a network. We would buy a switch which would have multiple ports. We can connect Wi-Fi router to that switch as well. It has antennas, right? So that your phones can connect to them. And then we bring wiring Ethernet cables from different floors, from different rooms, and we connect them all to this switch. And the Wi-Fi router is also connected to the switch. And then we have a special server that we buy, which is a very powerful machine, which is a computer, but we call this one a server. And we install all services on this server. So this server becomes a file server. We buy a huge storage and connect to this server. So we buy, let's say, a 5 terabyte hard disk in a small office, and you connect it to into this server. And we install a Windows server, which is a specialized server operating system, not a normal Windows 10 or Windows 11. So we install a Windows server on this machine, and it has a lot of hard disk. It has 5 terabyte, 10 terabyte, 20 terabyte hard disk, as much as we need. We install that on it, and we install file storage services in Windows Server, which is a feature on it. And then we can share in this computer's IP address with everyone. So all these computers can go to their browser, put in the IP address of this server, and they can access all the files on the storage device. So everyone can request that. So everyone is a client, because everyone can request files from this server, and this computer is a server. So compare that to a peer-to-peer network. I hope you understand the difference right now. Okay? So that's what a client-server model would look like in a small office. On the internet, this is also the same model. So except that these servers, these specialized servers, are somewhere in someone else's computer, and you connect to these servers. So for example, this server is somewhere in a different country. So you buy an internet connection, and then your clients are sending requests through browser using internet to this services to get YouTube files, YouTube videos, or other files, and it sends you those files, and then you watch it on your computer. So I hope this is very clear. Okay, it's cannot be explained more than that. Can a computer be both file and a web server? Can a computer have two services? Yes, definitely. So on this same server, you can have, for example, on the same server, I can connect, let's say, if you take the same example, I can connect a printer on this server, and then another computer can request to print a page, and it will print it for them. So at the same time, this server is a file server. At the same time, it's a print server as well. It's totally possible. It is only limited by what software that you have installed. Does it have that service enabled, or you just enable it? And do you have resources for it to run multiple services? That's all. Okay, right. So why do we follow this model? The reason why we follow this model is centralized control. So every time you have an issue with your files, you cannot access your files, or you cannot access your printer, you cannot print pages, the network administrator always knows that this is where the problem lies. This is what we need to troubleshoot. It is centralized. All problems are here. All management is here in one location. We don't have to keep running to different offices, different computers where the problem would be. We solve problems on the server side. So it's centralized. The control is centralized. So if you want to secure this thing, so we just secure this server side where our data is. So security is easy, management easy, control is easy, operations are easy, and it gives you scalability. How does it give you scalability? Well, let me get rid of all these things. Well, if you tomorrow expand, let's say today you had 5 client computers and tomorrow you have 100 client computers or 1,000 client computers. So this server would not be enough. So you buy another server and connect it here and add more storage to it. It's that easy to add resources because everything is controlled from a centralized location. So you keep expanding that centralized location. So that makes it easy to scale whenever our networks are growing. It is also reliable and it provides availability. It's reliable because you have dedicated servers with many redundant systems. As I showed you, you can have multiple servers. So if one is not working, the other would be working. And that gives you a higher availability and reliability compared to peer-to-peer network. For example, in peer-to-peer network, if you have one print server that is sharing a printer, if that computer goes out, you cannot print pages. Nobody can print pages. But in this case, you can have 2 servers with sharing the print services. If one goes down, other one takes over it. That's what we call reliability and high availability, that your services are not going down, even if a computer goes down. So here's a small animation that you can watch. You can see like this is a small network. This is an example of network. So you are in your offices and these are computers you're setting. There could be a voice or IP phone. There could be a TV connected to a network, and they all connect to a switch, and there's a server. So this is your internet connection. Your internet connections connects you basically to your ISP provider, which has a lot of different intermediary devices. So you can think of this as your home, and this could be someone else's home, your neighbor home, or somebody anywhere in the world. Both of these homes are connected using internet. How? Well, whoever whom is this is your friend in a different country, he has bought an ISP connection, an internet connection from ISP, and ISP has routers. Let's not get into what a router is, let's call it, there are intermediary devices that allows you or connect you to other people, right? Which is controlled by ISPs. And you have also bought a connection, an internet connection from another internet service provider in your country. And all these internet service providers are interconnected together using undersea cables, using satellite communication, using internet satellites, using point-to-point networks, microwaves, 5G antennas, 4G antennas, right? Which is something we will get into later, right? But they are somehow connected. And this is how your communication can work between 2 computers. You sit on your computer, you are the source, and this is the destination where you want to send a message from your computer. Let's say that's an email. So you generate that email, a message, and send it. It goes to the internet. On internet, you have intermediary devices whose job is to find where this destination is. Okay? And eventually this message reaches your destination, intended destination that you want it to send. This is what the basically internet is doing in simplest form, in easy plain English. This is what the whole internet is doing and nothing else. It takes your message that you are sending. You have to provide the destination address. Like this is the person or this is the computer I'm trying to send a message, and you just send it over to the internet. The devices on the internet that are interconnected, all the devices on the internet are interconnected using internet. These are intermediary devices. It is job of these intermediary devices to find out where this destination is, in which direction this message should go so that it reaches this device, and then eventually it will send it to the actual destination. That is the whole job of internet, and that is your job to configure and design everything in a manner that this gets done. That is your job. And we will be spending a lot more time on these intermediary devices. How are we connecting things together so that messages can reach from one source to another destination exactly as we expect it to be sent. We would be configuring these devices. We'll be choosing which type of links we need to have to interconnect them together. And we'll be running protocols on these devices so that these decisions, when a packet comes and it needs to go to here, how are these decisions made? How does it find, do I send it here or do I send it here? Which direction should I go? Which one would be faster? Which one would be slower? Which one would be more reliable? That's all you have to do. And this is what we're going to learn, okay? So what are these intermediary devices that are connecting other networks or your homes together? These are the intermediary devices. So far, when we were talking about clients and computers, what were we talking about? We were talking about these computers, the end devices, voice or IP phone, servers, computers, your mobile phone, tablets, TV, washing machine, air conditioner. Those are the end devices. We were so far when we were talking about client server model, peer-to-peer model, we were always talking about end devices, which we also called hosts. Okay. Now we are shifting our focus to intermediary devices. So what are the intermediary devices which interconnect all the end devices together and make them communicate? So intermediary devices are an important component in building networks. Intermediary devices interconnect end devices. For example, it includes switches, wireless access points that you have at your home. We also call them wireless routers because wireless access points plus routers, they act like both devices. Routers and firewalls. These are all intermediary devices. Why are they called intermediary devices? Because they interconnect end devices, as you saw in the previous slide here. Okay. So as you can see, these are the intermediary devices, all of these, including this. Okay, so these are intermediary devices. What are they doing? Why are they there? Their only job is to interconnect these computers, these end devices together. Without these intermediary devices, we could not have connected them together. We need these devices to interconnect them so that they can send each other messages. Think about your home. If you have two computers, two phones, mobile phones or tablets, if you want to send something from your one phone to another phone, you cannot do that without your Wi-Fi router. You have to be connected to your Wi-Fi router. So what is that Wi-Fi router? That is your intermediary device. You could send it via Bluetooth directly, or there are direct Wi-Fi connectivity as well, but that only works for small or limited time, right? You cannot scale that. In order to really scale, connect a whole lot of computers together like the internet or a whole world, you need these intermediary devices. So these include switches, wireless access point routers, and firewalls. So we talked about your home example as well. So the most important task of the intermediary device is to provide a path for the end device to communicate. That is its main job. There has to be some path through which your message should go anywhere in the world to reach the destination. So these intermediary device basically provides you those paths. But they would also have some other functionalities as well. It's not just giving you a path. It is also a job of intermediary device to regenerate and retransmit data signals. What does that mean? That means when you send a file on the internet, it's possible that it gets lost, it gets destroyed, it gets corrupted, right? Because it's just bits, it's just signals. So intermediary devices also can regenerate these signals and retransmit data signals on your behalf. So your computer doesn't have to do it again and again if it's lost. These devices will try their best to regenerate and retransmit and do their best job to deliver your message to intended destination. They also maintain information about what pathways exist in the network so that they can decide which is the shortest path, which is the fastest path. They also notify other devices of errors and communication failures so that you don't send, so if there's a corruption in the data, it will not send the corrupted data to the end device because it's useless. It doesn't have to do that. So it will notify you, your device, and let it know that whatever you were trying to send, it failed to send. It will also probably try to give you a reason as well why it failed so you can fix it. So all of these things are, somebody has switched on their camera. Whoever has it, please switch it off. I cannot see it, but I think other people are getting distracted. Yes, Peter, we could think of these intermediary devices providing pathways just like a road. So it is interconnecting and it's providing transportation. You are right. Now, we talked about two things, two components so far. We talked about the end devices here, here, and then we talk about the intermediary devices like this one, this one. But there's a third component that is necessary to create a network, and that is this medium. There has to be a physical pathway between these intermediary devices and end devices as well to interconnect them together. That is called the network media. There has to be a physical connection between them. So they cannot communicate, the intermediary devices and end host devices cannot communicate together without a physical media such as cable or a wireless connection. Even if it's a wireless, it's still a physical connection. So communication needs to transmit across the network on a media. There has to be a media through which this transmission could go. It could be wired, it could be wireless. In modern network, we have few options. We don't have a lot of options that we have to use. So we can use in wired networks, we have a lot more options. So for example, we use metal wires within the cables. That is the Ethernet cable usually. So Ethernet cable is basically copper cables inside, copper wires inside the cable to which we can transmit data. We can have a glass or plastic fiber, which is basically a fiber optic cable. So inside a fiber optic cable, the pathway is basically either created using a plastic material or a glass material, depending on the quality of the fiber optic cable, through which you would be transferring data using light pulses. And then you have the wireless transmission, which you are more familiar with because everybody has a Wi-Fi router at a home and they're communicating using wireless communication, which uses electromagnetic frequencies and modulation techniques to transfer data without wires. So you need at least one thing out of these three to transfer data between all the devices. So even if you're using a Bluetooth, you're still using a wireless transmission. It is just another type of electromagnetic wave. Okay. So we talked about three different things that consist of these. Remember, we're talking about network components. We talked about three things that are necessary in order to create a computer network. Okay. So we still have something left on the network media. Okay, so these network medias must have four main criteria of choosing a network media are these. So which media? So we talked about wireless media and wired media, and inside wired media, we talked about fiber optic and Ethernet cable. Which one you should use to interconnect all these devices together? Which one should you use to give them a physical pathway? Does this mean connect is different from communication? I don't know your question. Can you rephrase it? I don't understand your question. So if you rephrase your question, I'll answer it. So how do you choose which physical media you should use? Well, there are basically four questions you need to ask yourself. Yes, first you need a media to make the connection. You have to have a physical connection between two devices in order to do the communication. Otherwise, without a physical connection, there is no communication that is going to happen. The signals, the bits needs to go over some physical media. And that could be Ethernet cable, that could be fiber optic, that could be Wi-Fi, that could be Bluetooth, any of these things. So which one do you choose out of these? 4 or 5 options that you have, well, you have to ask yourself these questions. What is the maximum distance that a media can successfully carry? Do you use a fiber optic cable, or do you use Ethernet cable, or do you use Wi-Fi? Well, that depends on how far away you want to send a message. If you want to connect two devices that are just within 100 meters, you can use a Wi-Fi. But if you need higher speeds, reliability, then you might need an Ethernet cable. But if you have two computers that you want to connect that are two buildings apart, one is in one building, another is in another building, and they are 1 kilometer apart, then you can't use the Ethernet cable, then you have to use a fiber optic cable, because that can carry signal to multiple kilometers away. So that's how you decide which media to use. You also decide based on the environment, where it would be installed. You need to dig the ground to do the installation, or you can just run wires in the air, or is that not possible? Then you can use the wireless media. What is the amount of data? So depending on which media you select, that also gives you specific type of bandwidth and speed. So you have to be careful about that, and also about the cost of media. Fiber optic is more expensive, Ethernet cable is cheaper, so you have to consider those things. So these are different questions that you need to ask, based on which then you would decide which type of media we can use. Okay, so we talked about network components. We talked about host or end devices, which could have multiple roles. And it could be a server, it could be a client. In small networks, we have peer-to-peer networks in which devices can be clients or servers. But in most corporate environments or enterprise environments, you would see a client-server model where we have dedicated server for each service, which makes it a better choice for performance, scalability, security, and administration. So this is the type of end devices or network model you would be seeing in enterprise environments. This is created because using host or end devices. Then this is the first component of the network. Okay. Then you have intermediary devices, which are the devices that interconnect end hosts together. They also provide best path for data flow from source to destination. They also provide management of data, such as transmissions, finding errors. And examples of these devices are switches, routers, firewalls, and wireless access points. So that is your second component in order to create a computer network. And your third component is the physical media. You need a physical connection between intermediary devices and host devices to connect them together so that the signals or bits can be transmitted. We have different types of physical media. We could have copper cables, Ethernet cables, fiber optic cables, or wireless transmission in order to connect intermediary devices and host devices together. The media is chosen carefully by taking under consideration cost of the media, distance covered, environment, and amount of data it can carry. So I hope this is very clear from computer networks perspective that a computer network needs three components. If you have a host or end device, if you have intermediary device, and if you have a physical media, then you can connect all these things together. And whenever you do that, you can say you have created a computer network. It is that simple. So if you have a computer, a switch, and another computer, and you can use fiber optic cable or Ethernet cable to connect this switch computer and another computer with a switch, then you have essentially created a network. So this is a network. This is a computer network. Okay? Even if I remove this computer, it's just a switch, a computer, and a cable, Ethernet cable connector. It is still a computer network. But if I have a computer and I have an Ethernet cable that doesn't go anywhere, then that's not a network yet. In order for a network, there has to be at least two computers that communicate together. But notice I also said that even if you have one computer and one switch, it is also a network because this switch is also a computer of sort. So this computer and switch can communicate together as well, although it wouldn't be any beneficial, but it's still a part of a network. So the smallest network you can have, which is very useful, that would at least consist of two end devices, which would be interconnected using some sort of physical media, either wireless media or cable media. So I hope that is clear. Now, since now we know the computer networks could be as small as this, but this computer network could be as big as the whole world. So you have a computer at your home, then there are computers in the buildings. These could be one, two, or thousands of computers. And then you buy an internet connection, and there are other computers with ISP and other computers with other ISP, and these ISPs are connecting together using intermediary devices and so forth. And that becomes a one big network, which we call internet. So it could be a very small network, just like two computers connecting with a switch. That's also a computer network. It could be as big as the whole world. That is called the internet, which is also a computer network. This means we need something to represent these networks. How do we talk about these networks if we have a big network that has 1,000 devices? How do we even talk about how these 1,000 devices are connecting together? What are the IP addresses of these networks? What are the physical media through which they are connecting? What is the bandwidth of every media that is being used within the 1,000 devices? What are the models? What are the port numbers? What cables they're using? What are their configurations? How do we even start thinking about how the network even looks like, let alone trying to configure and accessing them and troubleshooting issues on them? Well, we need some sort of rules to represent these networks easily so that network engineers can communicate with each other about them easily. Okay, so that's why we have topology diagrams. So while knowing components of network is necessary to understand computer networks, it's also essential for network engineer to be able to represent the network in a diagram. So the type of a picture of a network is known as a topology diagram. So you have to have some mental image of how networks, how everything is connecting together. And that mental image, when you represent it on a paper, we call it a topology diagram, a computer network topology diagram, which showcases how different devices are connecting together. We can use free softwares. If you go to online.draw.io, or if you have Microsoft Visio, you can draw these topologies in there. It's very easy to do so. Different vendors also have different icons, representation of representing a computer, a router, a switch. You can download them and use them, or they are readily available if you go to Draw website. Then you can build these topologies. So we have mainly two topologies, diagrams to represent networks. One is called a physical topology, another is called a logical topology. Let's talk about a physical topology. So we can represent our networks using a physical topology where we focus on the physical properties of a network. So what would be a physical property of a network? So for example, where are the devices in which room? What are the number of the room? How many devices are there? How are they connected using a cable installation? How are the cables going through? What are the rack numbers? Which line they are? So this is an example of a physical topology of a small network. And you can see the properties of all the devices that this diagram is showing. It is saying that we have a web server in rack 2 shelf 1. We have another server, email server, in rack 2 shelf 2. So you see the information this diagram is giving us about this server is physical. Like, where is this server physically located, so that if I tell someone to go fix this server physically, he would immediately, by looking at this physical topology, know where the web server is. So he would have to go to server room number 2158, where he would go to rack number 2 shelf 1, and that's where the web server would be. So this diagram is basically giving me the physical properties of where the end devices are located, right? Similarly, This is these switches are placed in room 2124. So why do you need this diagram? So start thinking big now. Don't think about your home, because you don't need these kind of topologies for your small networks where you just have 10 devices. You can memorize those 10 devices where they are just by heart, right? But let's say you have a data center where we have 1,000 devices. Now you cannot memorize things. You cannot even communicate with your colleagues to tell them where the device is. It becomes hard. So that's why you need the physical information in physical topology, where you know exactly which server is in which room, because data center usually have different rooms and different racks, lines of racks, thousands and thousands of devices. They're very huge. Data centers are very huge, right? So this is how you maintain information. This is a university. So universities has a lot of rooms, a lot of buildings, right? So you would know, like, this laptop is in this room, maybe this is an office, this laptop is in a class 2, this is class 3, and there are multiple switches connecting them, and all have physical locations and physical information. So a diagram that gives you physical information about physical devices, I mean, this diagram could be a lot more detailed. Not all diagrams have the similar number of details, and it's still called a physical topology. For example, this diagram lacks information about what type of this cable is. It's just a black line. It doesn't give me the information whether this is a fiber optic cable or an Ethernet cable. It also doesn't give me an information how long this cable is. Is this 100-meter cable or 50-meter cable? It is also not giving me an information how is this cable running from room number 2124 to room number 2125. Is it going through the ceilings in the room? Is it going under the walls, behind the walls? We don't have that kind of information. We would still need that kind of information, and we can add that information to the same diagram or create a different diagram. It would be still called a physical topology, because still it is just giving you physical information about all your components, about your end devices, about your intermediary devices, and about your physical media. It might lack some information. You can create a second diagram for that. It just depends on how complex you want to represent the data in a single diagram, or you can just divide it into multiple diagrams. It is still a physical topology. You can also create this kind of diagrams instead of that one. It is also a physical topology, but specifically it's called then rack elevation. It gives you much more information about a single rack. And it's easier to build if you are just talking about a single rack where you might have 2 or 3 servers or 2 or 3 switches in one router for a limited number of devices. Then you don't need a physical topology like this. Then you get more information using a rack elevation. But if you have thousands of devices, then rack elevation doesn't work. Then you need this kind of topology. The rack elevation tries to show you exactly which type of device it is, what is it called, which port it is using to connect to exactly which port on this switch, and what type of model of this switch is, and how cables are going. So this one is showing that these are fiber cables. I can look it from here that these are fiber cables and these are Ethernet cables, and this is the power unit getting power cable from the power distribution unit, and so on. Again, it is still all physical information about how things are connected, where things are. It's all physical properties, so it's part of physical topology. Now we can have second type of topology, which we called a logical topology. It tries to not give you physical information about your devices, cables, intermediate devices, and end devices. It tries to give you information about logical configurations that are done on these devices. For example, if you have a web server, which network is it part of? It is part of 192.168.10.0. What is the IP address of this web server? For example, this diagram lacks that information, but we could add that information that, hey, this server has 192.168.10.1. This one is .2. This one is .3. So now we just look at the diagram and we already know what is the IP address of web server, what is the IP address of email server, what is the IP address of a file server. We also know which port it is connecting to which switch. And we also know which network it is part of. Similarly, for all other devices, we could mention the public IP addresses that we are getting from the internet. We could also mention the routing protocol we are running between them. So it's all logical configuration information, what is configured on these devices, which is not a physical information. It is configuration information, it's routing protocol information, it's IP address information. And when we look at this diagram, we immediately understand on the high level what is being configured on these devices. And that's called a logical topology because it's not related to physical properties of the devices. It is related to the configurations or logical configurations done on these devices. So it could be as simple as this one, or it could be as complex as this one. In which case it's, for example, these connections has this circle, they all have their meaning. I can look at it and I immediately know that ether channel was configured on these switches just by looking at that diagram. I don't have to look at the configuration of the device. So this diagram is telling me what is configured on these devices. So I'm saying, okay, I immediately know, okay, this firewall IP is 10.1.10.1, and it is connected to this firewall. And we have AT&T and MPLS connection from here. There's ether channel configured here. There's ether channel configured here. Ether channel configured here. I immediately know just by looking at the diagram. These are all configuration information that I'm getting. So that's called a logical topology. Okay. We will talk more about these things later. I'm just giving you high level discussion of what computer networks are. So topologies are diagrams that represents our computer networks. Physical topologies is a diagram that focuses on giving information about device names, physical locations, rack numbers, physical layouts of cable, and port numbers. Logical topology diagrams focuses on giving you information about device configurations, IP addresses, the protocols that are running on those devices, and how the traffic is flowing from which device to which device or which path it would take. Topology diagrams are important because it gives you quick information about complex network. If you have hundreds of devices interconnected together, thousands of devices internet together, in order to communicate or understand those devices, you don't have to log in and look at the configurations of 100 devices. That would take you days and weeks to understand. Instead, you would have these topology diagrams, and you look at these topology diagrams, and within 5 minutes, you know how everything is connected together, what type of protocols are configured on these devices, what type of networks, IP addresses are on these devices, and how the traffic would flow. And most of the time, 90 or 95% of the time, network engineers don't log into the device and run commands. They just look at the topology diagrams and think about logics. What is configured where, how we would configure new devices, where the new devices would get connected, what would be the IP address of new devices, and what configuration would go on the new device just by looking at these diagrams. So you'd be spending 90% of the time looking at these diagrams and brainstorming with other network engineers to make decisions. Okay. What software do they use? We already talked about Microsoft Visio, Draw.io. Let me show you. So this is Draw.io. If you go Draw.io, I have already logged in, so it redirects me to a new name. But let me show you that I actually went to Draw.io, and since I'm already logged in, it will just take me to the already diagrams that I have. So for example, I have these diagrams already in my file, and this is how we build diagrams and look around and add information. So in this case, you can think of this as a logical topology, but I haven't added the IP addresses information or device name so far. And you can just search a device here, like this is a switch. You search for a switch, it will give you different type of switches here, and you can just see why it's so small. Now it's getting better. So let's say this is a router, this is your wireless router. You pick it up and you can then search for a PC. And I have a bunch of PCs, so I'll just pick this one and you can just connect them together. And I connect it and you can say like, okay, this is a small network at your home. That easy. Okay. So we talked about why we need them. All right. So now you know how to create a network, what type of components networks should have. It should have end device as a host. It should have intermediary devices like switches and routers and firewalls. And it also should have some sort of media like physical cable or wireless networks. Having these three components, you can create computer networks, and you know how to represent them either using a physical topology or a logical topology. Now is the time. Let's not get into what type of switch. We have a lot of lectures and sessions waiting for us where we will be talking just about switch. In fact, in our very next session, we will go right away on a switch and we will configure a switch. But for now, let's focus on some of these high-level topics that we need to cover before we jump into those things, okay? So what are the different types of networks that are? So we talked about small networks, big networks, a network that consists of like a whole world is a network, which we call a network. But there has to be some classification of a network when we're talking about computer networks, where different properties, different types of networks will have different types of properties, right? So network comes in all sizes. They range from simple networks consisting of just two computers, that's also a computer network, to networks connecting millions of devices like the internet. It's also a network that has millions or billions of devices by now. They can be classified into different types based on various properties. So we can divide different networks and giving them different names based on common properties that have. So we have to pick which property we want to pick off the network based on which we will do classifications. So for example, the easiest way to classify a network is by their size. If you do classification by the size of the network, like is it a small network or a big network? Then we have small office, home office network. So if you have 5 or 10 devices, just like you have at your home, or if there's a small office or a home office, that's what we call a SOHO network. A SOHO just means small office, home office network. When we say a SOHO network, we automatically understand, okay, we are talking about a very small network where we might have just 5 devices. Or maximum 10 devices. That would be a very small SOHO network. And we already know in this kind of a small network, we don't need a lot of things. We don't need servers. We don't need high bandwidth. We don't need fiber optics. A small wireless router or wireless access point will connect all things together. And then we have worldwide network. And this is also based on size. So if you have a very big network, we call it a worldwide network. We can also classify networks by the type of infrastructure they have, the type of technology it's using. And based on that, we call them local area network or a wide area network. By infrastructure, what do we mean is that local area network has smaller infrastructure. It has centralized administration. All the devices in a local area network are owned by a single company or a single person. You go and buy all the stuff in local area network and you create a local area network. Everything at your home, you usually own it. All the computers at your home, you own it. The wireless access point, you most probably own it. You have paid for it to the internet service provider and you probably own it. You can go to a shop and buy a switch and connect all the computers together with the switch. That is local area network because you have owned it and you are administrating it. You are responsible for configuring it and breaking it and making it work. Wide area network is different, and local area network is usually very high bandwidth and very fast because you bought everything. Wide area network is different infrastructure. It spans across cities, across buildings, across the world, undersea cables, satellite communication, totally different infrastructure and totally different cost model. It's very expensive and you cannot buy it. You cannot buy wide area network because you cannot buy the whole land connecting one city to another city. Somebody else's land you have to use and dig up the land and run fiber optic in it. Then you have to pay the rent for that land. So that's why wide area network, usually you don't buy anything in wide area network, you usually rent it. It is slow, it is costly, it spans long geographical areas. So that's what we mean by classifying based on infrastructure. So when we classify networks based on infrastructure, we have LAN and WAN. We can classify it by type of access. Who has access to this network? In that case, we can think about intranet and extranet as opposed to internet. So intranet is kind of an internet, but for very specific people. Let's say for an organization, think about military use. So the military bases in your country, whichever country you are coming from, your country has military bases in, let's say, every city. How do you think they are connecting together? Do you think they are all using the same internet cables? Probably not. Probably they have laid their own internet cables, their own fiber optic cables from one city to other city, which is not shared with general public. Essentially, they are creating their own internet, but it is not allowed for general public. It is only allowed for military institutes to connect to. In that case, it is called intranet. Okay? So when you divide networks based on sizes, you could have a small home network, you could have a small home office network, which is a little bigger than the small home networks. And then you have medium or large type of networks in a building like a hospital or a university. That would be a medium large network where we could have hundreds of people, hundreds of devices to thousands of devices. And then even bigger network would be the worldwide network where different countries come together and connect together, which is where we start calling it internet. Okay? And if we divide network based on infrastructure, this is something I already talked about. Your home is usually called a local area network based on these properties, that everything at your home, you own it, you buy it, you have a high bandwidth, fast speed, and you are also responsible to configuring and fixing it. Wide area network, on the other hand, is something you cannot buy. Even though if you have a lot of money, you just can't. It has to be rented. It is ISP. It spans across cities. It uses fiber optics. And it uses specialized routers and devices. And it's rented to the public. So it has completely different properties. And that's why it's called wide area network. Everything at your home, in the building, in offices, in hospitals, they're all called local area network. How is internet made of, or what is internet made of? A lot of local area networks everywhere connecting together using WAN technology or WAN connections, or in other words, using internet. That's how everything is called internet. So inside the internet, you have local area networks and wide area networks, everything connecting together, all the LAN connecting together using WAN connections. That gives you internet, okay? So more things on local area networks. So I already talked about local area networks are usually confined to a small geographical areas like home or inside a building like a university or a hospital. Wide area networks infrastructure that spans a wide geographical area, usually connecting two different cities, two different countries, or the entire world. So you have hospitals, institutes, they're all local area networks. The other local area networks, to connect together, they need wide area network. And I already talked about like a lot of local area network in different homes, different hospitals, government institutions, schools, businesses. Everyone has a local area network because they have the same properties. They are in small geographical area. They own everything inside the local area network. They bought all the equipment, all the cablings. They are responsible for managing it. That's why they hire network engineers to manage their local area networks and so forth. But then all of these local area networks, for them to connect together using internet, they have to rent out wide area network from the ISPs who have built or laid out these wide geographical area connectivity between each other, connecting different cities, different countries, using undersea cables, digging rounds to lay out fiber optic cables, or using satellite. It is their responsibility to do that. You rent those services from them, and that's how all the local area network come together, connect using WAN, and they give birth to the internet. So internet is nothing but a combination of local area networks and wide area networks all coming together and connecting together. Okay. Intranet and extranets we talked about. So internet is the world, the whole world coming together, connecting for public purposes, civilians. Then you have intranet. Let's talk about intranet first. So intranet is company only. So for example, we talked about like a military bases in different cities. They can lay out their own fiber optic cable and they can connect together. That is also a network, but that's not a public network. That is only specific to that company or organization. So in that case, we would just call it intranet. Military in some cases can extend or allow specific organization with whom they work, like suppliers from where they buy stuff and they want to work with them. In that case, they extend some connectivity and allow some organizations or customer to connect to them. Then we call those extranet. But if we allow everyone to connect together, then we just call it internet. That just means it's now publicly open and for connectivity for everyone. Okay, so I think we spend a lot of time on this, so I don't have to review this, but you have the review items if you want to review it here. Now, the internet connections. We talked a lot about the internet. What is actually the internet connection? So, home users, remote workers, and small offices typically require a connection to an ISP, Internet Service Provider, in order to access the internet. When you say, I want to access the internet, what does it mean, do you think? It simply means you want to connect to everyone else. That's what essentially it means. So how do you connect to everyone else? Let's go, if we look at the previous diagram, where is it? This one. So if you come here or build a new home somewhere, so you have a new home, let's say this is your home now. You come here, you have a computer, a laptop, a mobile phone, and everything you bought. And you're sitting at home, but you're disconnected from the rest of the world. And you say, I will call an ISP and I'll ask them that I need an internet connection. What does it mean? In simple word, it just means that you want to connect to all these people, which is essentially the whole world, who are connected together. So the ISP would come up and they would already have laid their fiber optic cable in up to your street. It's already in your street. You just call them, they come here and they give you a connection to your home and put an access point here, and through Wi-Fi, your phone connects to this Wi-Fi and it finds its way through this internet connection to everyone, anywhere. It can go anywhere in the world now. That's simply an internet connection. Okay. So this connectivity that the ISP could give you to your home in your street where they are already present, that can be done using many, many ways. And the technology has evolved throughout years, throughout the decades. So the internet service providers usually had a lot of different options in order to let you connect with the rest of the world, or order to connect you with it simply saying internet, right? They could have DSL technology, a cellular service if you're using a 4G or 5G connection that's also connecting to the internet and to the rest of the world, but using a cellular service, a 5G service. You can also get a fiber to the home connection, which is most common one these days. You could also get a satellite connection, let's say where the SpaceX satellites connectivity is available. I forgot its name. What is the name of that technology from the SpaceX that is giving internet using satellites? So you could get that. So why do we need internet? Organizations usually need access to other corporate sites or branch offices, and as well as the internet, fast connections are required to support business services, including IP phones, video conferencing, data center storage, streaming, going to website. Yeah, Starlink. Thank you, Sahal. So Starlink, you could use Starlink to get connectivity to internet. That would be an example of satellite internet connection. So these options are for home users, okay? So if you are a home user, you want internet connection, you can get Starlink, you can get fiber to the home, you can get cellular service, you can get DSL. Most commonly, you would get fiber to the home connection these days. But organizations need different types of connections because these home-based connections, they are cheap and they are shared. They are not as fast as the connection that organizations need. Organizations need dedicated internet access with service level agreements, SLA. Your home-based connections that you get from the organization, you don't have SLA. SLA means service level agreements, meaning there is no agreement between the ISP and you as a home user where they guarantee you that this internet connection will be up the whole year. And if something would happen to it, they would immediately come and help you. They do claim they would do, but they are not legally bound to do that. So if something would happen to your internet connection and it's not working and you would call them up, it might take them 1 day. It might take them 3 days to come up and fix your service, depending on how busy they are. And you can't do anything about it. But organization cannot take these kind of risks. So ISPs have SLAs, service level agreements with these organizations where they say if something would happen to your internet connection, we would try to fix it as soon as possible on priority basis, maybe within 1 hour or within 3 hours, because internet connections for organizations are very critical. Their economy, their budgets, and their finances depend on these type of connections. So they get dedicated internet access with better services, better speeds, service level agreements, lease line connections, and different types of internet like Metro Ethernet, MPLS, etc., etc. And they are very expensive as well. You don't get this kind of service cheap, right? So this is expensive. So remember, there are two types of internet connections. One is for home-based user, which is shared for general population, and other are specialized connections that are called dedicated internet access. They're usually called DIA. Why are they are expensive? Because they have SLAs, service level agreements, and you might get 100 MB or 1 GB speed here. It would be cheap, but here for the organization, even the 10 MB speed that they get could be multiple times more expensive than the 100 MB you are getting at home. But the difference is that your 100 MB is not guaranteed. You might get 100 MB, you might not get 100 MB. When you check your speed, you might be getting 50 MB, depending on how many people are using, because it's a shared network. But in organizations, when they get dedicated internet access with SLAs, if the organization says it's 10 MB ISP, this must always be 10 MB. It's not shared with anyone else. It has to be 10 MB throughout the year, regardless whether the organization is using it or not. That's why it's expensive. So it's the same thing that is being discussed here. I already talked about those things. At home, you might get fiber to the home, DSL, or cellular networks. And these connections, even if you buy a 50 MB, they're not always 50 MB guaranteed. You might get 50 MB, you might get less. That's how the home and small office internet connections are. Business interconnections, if you buy a 50 MB connection, it is guaranteed to be 50 MB connection all the time. Okay? So there are also service level agreements to ensure this connection will be up 99.99% of the time. The type of dedicated internet connection for organization is called lease line. So that's one type of it. These lines are reserved circuits within the service provider's network that connect geographically separated office of private voice or data networking. The circuits are rented at monthly or yearly rate. So this is one type of dedicated lease line that you can buy from ISP. There are another type of line which is called Metro Ethernet, which allows, so these are the type of services, WAN services. So for example, there's a bank. They have a headquarter in, let's say, New York. And then they have a branch in Chicago. And then they have another branch, let's say, Washington. And so forth. They would have many branches in different cities. They could have 200 branches. All these branches want to connect with the headquarters. Now, you could buy an internet connection on all these branches in headquarters and connect using internet, but that would be slow. They want to communicate together. They don't want to communicate with the world. They want to communicate together. So the ISPs have different types of services like dedicated lease lines and Metro Ethernet, which are specialized WAN connection. They're not internet connection because they're not letting them to connect to the internet to the world. It is just letting them to connect together from different cities. So they have already laid out fiber optics to the different cities, and they give you these dedicated links on a rent basis, yearly rent, in order to connect your branches together to the headquarters so you can communicate together on high-speed communication without going to the internet. Okay? And then you could also use the internet as well, but there is a business DSL, which is a better than the home-based DSL that could be also used. They can also use satellite connections as well, but not as common. Okay, question. So please. Yes, Joseph. That's also possible. Dark fiber. So basically, dark fiber means like an ISP has laid out a fiber cable from one city to another city, but nobody is using it. It's empty. And you, as a bank, if you have a branch in one city and another city, you can just talk to the ISP to rent out that fiber optic and ask them that I will be using it. And it's dedicated only for my organization. And you pay the rent for that dark fiber. The ISP owns it. You pay the rent to use it. Correct. That's dedicated cables for them. Okay, converging networks. So the trend that we had previously was that if you remember from the old homes, you wouldn't have it now. We had different networks. So if you remember, even some homes would have it right now as well. We had cable TVs. So when you had cable TVs, you had to run. So if you had like 3 rooms and you had 3 TVs in your room, you would have to run the cables, the coaxial cable for the TV cable to all these 3 rooms in order to connect them and get the cable TV, right? So the cables that you were running through your house was a separate network specifically for your cable TV. With a specific cable, a coaxial cable was used. And if you have multiple phones, landline phones, you would have a different network, different type of cable running for phone lines to different rooms, creating a separate network for the phone lines. And then came in the computer, and then you would be running, if you had different computers in different rooms, you would be running a computer network cables like Ethernet cables or fiber optic cable to different rooms. So in the same building, you would have 3 different types of network. One network for just landline phones, another network for cable TV, and another network for computers. But that trend later on changed because the computer networks started supporting the TV traffic as well, the voice over IP traffic as well. So you no longer need landline network for telephones. You no longer need cable network for televisions. You just need one network that can support all this type of data. It can support, where's my mouse? It can support communicating to different computers using data. It can support voice or IP communication. It can also support broadcast or cable TV networks as well, video data essentially. So that's basically called the converging network, that the networks are converging. Previously you had different networks for different types of data. Now all the data goes through the same type of network, which is the computer network. It supports voice, it supports video, it supports normal data as well. That's what conversion means, that they have all converged into a single network now, which also means that single network is being used for all sort of devices. You're connecting computers, you're connecting voice or IP phones, you're connecting computer devices or televisions. That means you need more bandwidth, more speed, because everything is using the same network, so you need more bandwidth in order to support that data, voice, and video. Okay, that's the converged network. All right, so let's go and download and install Packet Tracer and see how we can do that, because that's where we would be, everything we're learning, we would be practicing there. So if you go to your class in module 1, which is what we are studying today, everything I'm showing you is already in here in your account. You don't need slides, just go through your chapters. If you're going through slides, that's not for you. You're missing a lot of data, you're missing a lot of information. Go through the course, that's for you. So in 1.03, we have download and install Packet Tracer. It gives you a link, click on that. And it will take you to download the Packet Tracer, the latest one. So here you have it for Mac OS, for Windows, for Ubuntu. Packet Tracer 9.00 is the latest one. So you need it for Windows. Let's say in my case, it's for Windows. I'll just download this, click on that. It already started downloading. So once it's downloaded, just have to double click on it, install and follow the instruction, do next, and it will be done. There's nothing special about this application. It's just like a normal software. I wouldn't be doing it again, so I'm canceling it out because I already have it installed. There's nothing special about it. I'll just search for Packet Tracer in my computer and click on Cisco Packet Tracer, and it will just start. And this is Cisco Packet Tracer. It opened up. So the first time you would be opening it up, most probably it would ask you to log in. That would just mean to log into your Netacad account. Or if you don't want to log in, there will be an option to use it as a guest. You can do that as well. So there's nothing special. It's a normal software. It has the installation just like any normal software. Now let me zoom in on this. We think it is too small. Toolbars, bottom. I don't know how to zoom in this toolbars, but I hope you can see this. So in Packet Tracer, we have two types of views. Oh, well, let's not talk about views. This is where we would be building our networks and topology and devices. On the bottom left, you could see there is a section called, if you hover over it, you can see it gives you different names. Like, for example, this is saying network devices. You come here, it says end devices. So it's the same end devices we talked about. If I click on end devices here, in this section, it opens up different devices. So it's showing me like inside end devices, we have these end devices. If I click on that, then it gives me a whole list of end devices that I can select off. What are the end devices we talked about? They could be PCs, they could be laptops, they could be servers, it could be a media server, it could be a printer, it could be an IP phone, a voice or IP device, TV, tablet, a smartphone. These are all end devices. We can make them connect together and communicate. So this is one component of building computer networks, right? Then we have intermediate devices like these network devices. I click on, so there are a bunch of other end devices as well. So this is home-based end devices. You can select home. So these are IoT devices, bulbs, lights, fans, AC units. We have Bluetooth devices, a bunch of IoT and industrial level devices as well. Okay. And if you click on the network devices, we have intermediate devices in which on the bottom now things change. Now I can select routers. And if I click on routers, I have a bunch of different routers here that I can select. You can click on switches and I have a list of switches that I can select from. The switches. This is a router. And this is other hub and repeaters. These are wireless devices, a Meraki device, a wireless router here, like you have at home. There are firewalls here. There's a firewall. So these are all the intermediate devices we talked about. And then you have this lightning bolt called connections. And if you come here, we have a bunch of different types of physical media through which we can connect. So this is called console cable. This is called copper straight through cable, a copper crossover cable, a fiber cable, and so on. And we can connect different devices together, intermediate devices using this physical media. That's how we build networks. Okay. So easy with your questions, guys. I mean, you're asking a lot of questions in the chat. I'm going through the same thing. You're throwing questions out of nowhere, like somebody's asking, can you show a CLI, please? Like, do I stop whatever I'm showing you and just answer your question to show you a CLI? Think about it, okay? Because you're distracting other people. Everyone is reading your chat and you say, show me a CLI. So we are going through it. We will see it. Just have some patience, okay? All right. So whatever we do here is basically, so let me just get rid of all this now. So I was just showing you how we can work through it. So let me just select all of this and delete it from here, okay? So let's create a very small network for us. Like let's say we have 2 laptops who bring a switch and connect 2 laptops together. This, okay? They're connecting, the links are coming up. Let me just add a router as well here and connect the router here as well. That's it. Okay. So if you focus here, it is basically showing you, see if I can show some preferences and show device model labels, device name labels. That would be better. Okay. So what we are seeing here, let me mute everyone because okay. So what you see in here is called logical topology. If you see in this top left side, it says logical. Whatever I'm building here is kind of showing me in a logical topology, in a sense that it's not giving me any physical information at all. It's just giving me an information that these devices are connected together somehow using a black line, which could be anything, which could be a fiber, Ethernet cable, let's say. And what port they are connecting, I don't know. And it's basically showing me a logical view of how things are connected, not necessarily how they're physically connected. Are they in the same rack or a different rack? Are they in the same room or a different room? Right? Or so we can switch over to physical view to see that, and we'll do that in a while. But before that, on each of these devices that you are working here, you can just simply click on it, and then you can see, I think that is in sound. Let me think I opened up sound in place sound. Yeah, close these sounds. Okay, so you can click on these devices and it will show you a physical view of this device. You can zoom in on seeing like, hey, this is a router icon. This is a topology diagram icon where we say this is how a router should be represented in diagrams. Router are not really like this. This is just a representation of router. Router looks like this. So this model of Cisco, this is Cisco 4300 series router. This is how it looks like. It has 4 ports here. It has an on-off button. I can switch it on and off here. It has a power distribution cable. It has a console cable, USB port, serial ports. It doesn't have a serial port, but it has 4 Ethernet ports. And you can add some physical modules here. These are things that we can talk about later on. And we can configure this device. Right now it's still booting, and we can go to a CLI tab to see how it looks like it's CLI. And we can access CLI now. We can configure this router using a command line. Okay. Similarly, for a switch, you can click on a switch. It shows us how this switch, this particular model of switch that we selected, how does it look like? We can zoom in on it. We can see it has 24 ports, 24 normal ports, 2 uplinks. This is how it looks from front. This is how it looks from back side. It has a power cable. It doesn't have an on and off button in this particular model. Switches usually don't have that. So if you have to switch it off, you just unplug it. It has a console port for management. It has some status lights here, and it's called Catalyst 2960 series switch. This is exactly how it would look like in physical world if you buy a Catalyst 2960 switch. But in a logical topology, we use this image for a switch. It's a representation of switch for easiness to show how this is a switch. Similarly, if I click on a laptop, it shows me this is how laptop, this is not how actual laptop looks like. This particular model looks like this. It has an on-off button. It has a Ethernet port here. It has a jack, a headphone jack. It has USB ports, a mic jack, and you can configure a lot of interfaces. We have desktop application, just like you would log into a computer or a Windows or a Linux machine. You have a terminal to access this, command prompt to access this computer. You can run commands. It has C directory and so forth. It has different applications installed on it. It has an email application, Bluetooth application. It has TFTP services. It has command prompt. It has a browser. You can browse through this computer if you have internet connection or created it. You can put in a URL, for example, but it wouldn't work, right? Google.com is not reachable because we don't have a Google server in this topology. But if we can deploy a Google server, which we would do, then we will be able to go to google.com as well. Okay, so Packet Tracer is essentially creating a real-world simulation in this small software where you can play around with different models of switches, different models of router, different computers, laptop, mobile phones, internet connections, Wi-Fi devices, access points, routers, and connect them, bunch of these things together and configure them and see how they would behave. So you can do everything that is required of you in your CCNA exam topics. All the simulation, all the lab practice can be done inside the software without ever touching physical devices. Now, that doesn't mean that I'm recommending or suggesting that you never use a physical device. Using a physical device, if you had an opportunity to look at the physical devices, please do so. If you can purchase it and practice with it at home, at least buy 2 switches and 1 router. That is recommended. Do it. If you have the money, you can do it. If you have some friends working somewhere in some institute, in academy, at a university, just go with him, ask him a favor, and just go and look at a rack. How do these physical things look like? How do these cables connect together? At least do that. It is important to see them physically working so that you have the right amount of expectation or right image in your head when you're talking about routers and switches. Okay, so we're not configuring anything. We're just going through a demo of a packet tracer, what a packet tracer is. For those who don't know, this is what a packet tracer is, and this is how it works. So once we configure it, we can actually see packets. So there on the bottom right side, you can see this is real time, meaning if I ping a computer, this computer to this computer, send a packet, it will simulate it as a real time. Like in real world, if you type google.com in a browser, it loads up in 1 second, right? That's what real time is. But we also have a simulation where we can select different types of protocol where this packet tracer turns into a slow-mo like tool where when you type google.com on this laptop, it would not happen in real time within 1 second. It would show you step by step a packet being generated, a request being sent, going through this cable, going to a switch, then going to a router, then going to a server, then server processing it, creating another packet, responding back. It will show you in a slow motion, step by step, how this communication is happening in these devices. And that's what we will be going to do when we are learning how these protocols or these devices behave when we configure them. That's what we would be learning. So back to real time. So you can switch over between real time and simulation. Similarly, you can switch over between a logical topology and a physical topology. So over here now, I'm going to a logical topology to see how the physical topology would look like for this logical network that I built, where I have two laptops connecting to a switch and a switch connecting to a router. How would that look like in a real physical world? Because this is not how it would look like in a real physical world. This is just a picture, a representation for our high level understanding how things are connected. But it does not give me any physical information. Where is the router? How does the router look like? Which port the router is connecting to a switch using which cable? In order to look at that, I will switch over to a physical mode. So in the physical mode, it is giving me a whole city-like view. Inside this city, this is my city. I go to my home city. Inside city, I could have a lot of buildings. This is a corporate office, my office. Inside my office, there are a lot of rooms. And inside this room, there is a main writing closet where I can see two laptops already connected. So let me just go inside the closet. So this is the wiring closet. So usually your laptops would be sitting in your office and cables going from this from these laptops going into this main wiring closet. It could be a small room inside an office where I have racks. So if I go to that room, I can see that there's a rack in that room. Inside this rack, I have router 1 and a switch 1 that I built over. So if I go back to logical, this is router 1, this is switch 1. Let me go back to physical. I see router 1, switch 1. I can carry it, change its position here. It doesn't make any difference here because it's not showing me any physical information at all. I'm just looking at this. It's telling me that router 1 is connected to switch 1 port 3 here. I can manage cables here, so it doesn't show me. So it's now managed going through the back, but it's still connected. I can just say unmanaged and it shows me right here. It's just a way to get it out of my way. If I hover over it, it gives me more information about a specific cable. What is the source device? It's connected to laptop 1. The port is Ethernet 0. It's connecting to a destination switch 1. The cable length is 21 meters. The cable type is copper cable, copper straight through. So it's giving me a bunch of physical information now. Similarly, if I move around this switch somewhere like this, it doesn't make any difference here. It's still the same switch. Okay. I can delete these laptops or switch from here, let's say, and it is gone from here as well. Now I just have one router. I can delete these laptops and they're gone from here as well. So if I go up arrow, no more laptops. I can also do same things here. I don't have to go to logical topology and add them here. So for example, I go to computers and I'll put a PC here. So in order to put a PC here, I would just need to bring in a desk or something. So let me get that. Need to put it somewhere. Let me just get a server here. So I will put a server here, and I'll put a switch here. So here's the 2960 switch, and then I can connect this server and switch together. So let's say I can connect in. Let me zoom in. I can get a cable connecting it from here to here. And similarly, I can do it between switch and a router, connected from here, here. And now they are connected. I can move it around like this, and I can click on this router. It opens up its CLI. I can do everything from here as well. Okay. And click on switch. Can right click on it, inspect the rear to see how it looks from the backside, how the server looks from the backside. This is the backside. I can inspect it from the front. This is how its front look like. This is manage all cables, and you can do. And if you go to logical topology, and you can see that you have connected switch in a server and a router together. Okay. So we will be spending a lot of time in physical mode. In logical mode, we'll do explorations. This was just a quick way to show you how we would be working in Packet Tracer. And in fact, I will give you a little homework where you can go through this video, and you can watch this video to understand a lot of other aspects of Packet Tracer. And you can also download this logical and physical mode exploration. Just download it as a file. I showed that yesterday as well. And then double click on it. It will open up in Packet Tracer, and you have all the instructions to follow. And there's nothing in this lab. It's not making you do anything. It just helps you explore different options that are available in Packet Tracer, so you are up to speed. Okay. So I hope now you're able to download and install and navigate through the Packet Tracer and understand how we would be going ahead in our Packet Tracer. Okay. So in the beginning, I'm going to finish up this session. I know it's getting tiring now, so I'll just wrap it up. Just quick things that we talked about network architecture, that we now know how networks look like, what consists of a network, what devices we need, what are 3 type of devices that we need, and you can skip the knowledge check, it doesn't matter. So in network architecture, we just don't need, so when you rely on your networks, you just don't want it to go down ever, right? Because if network goes down, as we talked about it, your whole life is depending on it, right? So you don't want it to go down, which means you want your networks to be reliable, right? A reliable network never goes down. So how do you make sure that your networks are reliable? How do you make sure that your cables would not just disconnect and it would disconnect you from internet? How will you make sure that your router would not stop working? Okay. So in order to have a reliable network, not just a normal computer network, a reliable network, your network should have these characteristics. It should be fault tolerant. It should have scalability. It should have quality of service. It should have security. That's how you make sure that your network is reliable and it would not go down easily. It would not disconnect you from internet. If there is a failure, which there will be because every physical things have failures, there will be failures, but if you make sure that your network has these 4 characteristics, even when there are failures, you would still be able to connect to the internet and work and rely on your network, okay? So let's see, how can you provide fault tolerance in your network? Well, what is a fault tolerance? Fault tolerant network is the one that limits the number of affected devices during a failure. So because failures would happen, you cannot stop failures from happening. Failures would happen. You can only plan already ahead of the time what would happen when the failure happens. And to do that, what we do is that our network, we don't depend on a single device. We always create multiple paths between source and destinations for the messages. So if one path fails, the message can instantly send out using a different link. That's how you make fault tolerant networks, that you have multiple paths. You do not rely on a single path. Okay. So packet switch networks are by nature can follow multiple paths. Because they are packet switch, all the information is divided into chunks, which are we call packet, and then they are switched out through different paths. They don't follow the same path, okay? A single message such as an email or video stream is broken into multiple message blocks called packets, and then each packet has the necessary addressing information of the source and destination of the message. The routers within the network switch packets based on the condition of the network at the moment. That means that all packets in a single message could take very different paths to the same destination. Your same message where you say hello everyone could be divided into 3 different packets. Each packet could be taking a different path to reach its destination, and the destination will combine it together and it would read hello everyone back again. Although everyone took different path, it still comes to the same destination. So this is how a fault tolerant network looks like. So all your computers, voice over IP phone, they have multiple paths in order to go out to the internet. One is this, another is this one. So usually it takes this path, but what if this device stops working? What if this cable stops working? Well, it will automatically go through the second path if available. So that's why when you are designing a network, you will design a fault tolerant network. If somebody tells you to design a network and you say, okay, you have a computer, I will buy a switch connected to the computer, and then I'll buy a router, and then we'll ask the ISP for the internet connection, and we'll get that connection and connect to this router. Is this a good network? Would this network work? Yes, it would work. Is it a good network? No. Why? Because it's not fault tolerant. What if this router stops working? What if this switch stops working? What if this cable stops working? What if this internet stops working? Any failure at any level, at any device, on any cable, and you don't have internet access. Okay, so that's why when you're designing a network, you will create a fault tolerant network. You would not tell your employee to buy one switch, one router, one internet connection. You would always tell it, look, buy multiple switches so we can connect our computers to different switches, multiple routers, so these routers are connected together, and buy 2 internet connections from different ISPs so that my computer can send messages using this path. And if anything would happen to this cable internet connection, this device, this switch, I will always have a second path to go out to the internet. Now that's a fault tolerant architecture or network. And as a network engineer, it is your job to advise and create these or design or architect these kind of networks. Because if you're saying to buy a switch and a router and connect it to the internet, you're not a network engineer. Anyone could have said that. Everyone knows to buy a switch router and connect them together and you would get internet access. Your job as a network engineer is to create fault tolerant network. Okay. Then scalability. You have to design your networks so that they are scalable networks and expand quickly to support new users and application. Okay. So to do that, you would need to design your network in such a way, just like this one, where you can add simply more devices. So for example, if there are another department, you need to connect 10 more people, you don't have to make a lot of changes. You would just buy another switch and connect 10 other users here. So you'd have to design your network where you plan this ahead of time. You're not thinking about it later on when 10 new users come in and your employers for your organization say, hey, we have 10 more computers to be connected. And then you say, oh, I don't know how to connect these 10 users. Now we have to change our whole architectures because I did not think that more 10 users would come. I had designed it just for 50 users. You cannot say that. You have to think about scalability already when you are designing a network. So if somebody tells you to design a network for 10 users, you would not design a network for 10 users. You already should be thinking about scalability, that, hey, what happens if after 3 months or 6 months, they tell me that our users are increased from 10 to 50. Then what? You cannot be changing network designs in 6 months. So you should have thought about that this would happen. Okay. Quality of service. Now that you have thought about scalability and fault tolerance, the third characteristics of a reliable network is to have a quality of service. Quality of service means you would have new applications available to users over networks, such as voice and live video transmission. So when you have people connecting computers, right, and they're connected to the internet, not all users have same usage. This person A might be just browsing and downloading files the whole day. Okay, the person B might be using Microsoft Teams, doing meetings, right? Or conferences, conferencing tools and connecting. And which person would be more important? This one, person B, because he's using Teams and meetings, that means he's using voice and video data, which needs more bandwidth, reliable network. The browser person who's browsing, going through different websites and downloading files, his data is not as important or as sensitive, I should say, not important, but not as sensitive. So you should be able to configure quality of services in your network where you give more priority to people using video and voice data and low priority to people using browser and downloads, which is simply using normal data. Why? Because if browser slows down or their download slows down for 2 or 3 seconds, that doesn't make any difference to them. But if your voice or video streaming slows down, then they cannot talk, they cannot have meetings, they cannot have calls, and that affects them. So it is your job to think about quality of service. You can configure quality of service on these devices, on switches and routers, where you prioritize voice or IP and video data over the normal data, so that if there is a congestions and bandwidth limitation, speed limitation, which one takes priority? Your voice and video takes priority, so that they don't have issues. That's quality of service. Okay, so this is an example of quality of service that you can configure on this device, so that the data coming from voice or IP phones, they get priority and get to internet, and these people using computers, using web pages, they get lower priority, because it doesn't matter for them if their page loads a bit slower. And finally, the fourth characteristic is network security. You don't just create a network without thinking about security. If people get hacked, that is because of you, because you had a poor design, you did not consider security, you did not think about infrastructure security or information security. So that's also an important part of it. Whenever you are designing a network, you have to think about fault tolerance, quality of services, network security, and scalability. You cannot be an architect or network engineer without thinking about these things. Okay. So more on security later on. This is a review of so far what we've done. So you can go through that again. So I'll go through these final steps very quickly, because there's nothing technical information. What are the recent trends? Well, the recent trends are that people are bringing a lot of devices to the organization, which is called bring your own device. So initially, organization did not allow you to bring your own laptop to office, because it's not secure. They cannot control your laptop, what is installed on your laptop. It could have viruses and so forth and so on. But now trends are changing. They cannot stop you from bringing your phone to your office, for example. So now they have to think about that. You must bring your phone to office, and you would then need Wi-Fi access to connect your phone to their network, which again exposes them to new threats. It's risky, but now they have to manage that. They have to consider that people will be bringing their own devices to office. How do we control that? How do we be secure? Online collaboration, there is more and more voice and video data because of online collaboration and meetings, because of these tools like Microsoft Teams and Zoom, video communication, and people are accessing a lot more cloud computing data from AWS, Azure, and SaaS applications. So in your network, you have to think that people would be doing this. This is the trend. This is what people do on their laptops and computer. You have to create a network and design it, thinking about providing them quality of services and security based on what people bring and what people use in your network, right? Bring your own devices exposes their network to more threats, so they have to think about security more and more in their network because of you bringing devices to their organization. Online collaboration means more and more high bandwidth data is needed, more reliable networks are needed, and high quality of services for video and voice packets is needed in your network. So that should be part of your network design. Cloud computing reliance means that you have to think about that people are no longer just using networks to communicate or do file sharing or printer sharing. People are using uh, the internet to access all these things from the internet, from the cloud. So things are hosted on the cloud, so you have to give them reliable internet, high-speed internet, so that they can access files on the cloud, not just locally with each other. There are different types of clouds. These are some of the things that we will discuss later on. I don't want to overburden you with that. There are other different types of technologies are using in home. People are more relying on home-based networks. There is power line networking that is also possible. You don't need to get deeper dive. I'm just giving you an example. These are also types of networks. You should be just knowing that even the power lines in your home, there are new technologies that they can use those power lines, the already electrical lines that are running in your home, that could be also used for devices to communicate together without needing a separate computer network, which is a newer technology. You should just know that it exists. Okay. And network security. This is something we have a whole chapter on it later on. We'll be talking about network security in depth, but for now, you just need to know that when you're designing a network or architecting them, think about security threats. There are different types of threat whenever you connect to the internet. There are viruses, worms, and Trojan horses. When you are going and downloading files, you might be downloading these things. So you have to secure your networks from these things, zero-day attacks, threat actors. These are some of the things that we have a whole chapter on where we will be talking about these things, okay? So how do we save ourselves from these kind of things, these kind of threats on the internet? Well, we have security solutions. We have firewalls. We have antiviruses software. We have anti-spywares. We have intrusion prevention system, intrusion detection system. We have VPNs, access control list, dedicated firewall system, which is all the things that we would be talking in a separate separate chapter, okay? So this is the end of module 1, which was networking today. It was just to give you an idea of what networks are, what are the components of networks, what are the different types of network, how the internet is built, what is internet, how we are going to practice everything we are talking about. So we look at the packet tracer, which has a logical topology, physical topology, it has real-time and simulations. We can do everything in packet tracer just like you would be doing it in a real world. So that's how we would be practicing throughout this course. And the next one is basic switch and end device configuration. So from the next class, we're jumping right into the switch and start configuring the switch, okay? So next class would be very interesting. So I hope I will be seeing you all in the next class, and I'll be providing recording for this one in the group. Now I open it for question and answers. If you people have some questions, you can ask this question now.
Musa,
Yes.
I would just want to make a recommendation. I guess you give the lectures and everything. We have about, like you're doing now, have 20, 30 minutes at the end to ask questions, so you're not people not disturbing the class. Would that be a better idea?
That is actually the idea, yes. That's how we do
I'm
it.
just saying that I think one you were giving the lecture where people were like asking questions. I think either if it's related to that specific set of training material, I guess people put their hand up and ask question, or just if they can just make a list of questions and just ask at the end of last 20 minutes. You dedicate that 10-20 minutes to question time.
Yes, that is correct.
I'm just suggesting that.
Yeah, no, this is how I have planned it together. So people are doing chat, so throwing a lot of things in chat. If it's too distracting for you, just don't look at chat. I'm taking my session and I'm not looking at the chat a lot of the time.
Okay.
If I see a question at the chat time, I just answer it, but I'm not answering everything from the chat. I'm giving everyone a chance at the end of session to ask any question.
Okay, that's fine. Thank you.
And I will also be not answering questions that are not related to the session. So for example, someone right now is asking me SD-WAN question. There's nothing we talked about SD-WAN. Why are you asking me SD-WAN question? We have topics for every day. So I cannot just randomly ask you cannot ask me random questions about SD-WAN or data center when we are not even studying that right now, okay? Because otherwise, like, yeah, let's talk about BGP, right? so that doesn't make sense. Like everyone, there are a lot of people with different level of knowledge coming here. They already cleared up that in previous session that there are students who doesn't know anything. They have never heard about SD-WAN. They never heard about BGP. They're just starting. So I have to take everyone together. So please don't just throw in question. You would confuse people. You would scare people who are just starting, right? We just got started. It's our first session. So please don't ask BGP or SD-WAN questions. All right. Yeah, I think I would have to now look for that setting where I block the chat because it is becoming very distracting. But I hope we will figure these things out. People will understand it was first class, so people don't know how to ask questions. But I think it will be sorted out. I can block people's. I can mute everyone's mics. That's not a problem.